All right, recruit, listen up. This is your first classified briefing at the Hawkins National Laboratory. Everything you're about to see is top secret. Your mission, should you choose to accept it, is to understand the invisible forces that hold our world together and, well, the one that's lurking just underneath. Your briefing starts now.
One of our field agents said this right before we lost their signal. A scream. What does that even mean? It means energy, right? A release, a change. But a change from what? What kind of hidden, volatile world is going on inside every single atom to cause something like that? Today, we're going to declassify the truth. So, our first file. We're peeling back the layers on reality itself. We're declassifying the fundamental structure of matter. And here's the first big secret. Just like this quiet little town of Hawkins, the atom is mostly empty space, but it's hiding a furious, incredibly energetic core. To give you some scale, imagine the nucleus as a tiny marble sitting on the 50-yard line of a giant football stadium. The electrons, they'd be like little specks of dust flying around the nosebleed seats. That's how empty it is. Now, the number of protons, we call that Z, the atomic number, that's what decides an atom's identity. It's what makes it hydrogen versus, say, uranium. And the total count of protons and neutrons, A, gives it its weight. Now, messing with those electrons up in the stands, that's just chemistry. It's predictable. But if you mess with that marble on the field, that's when you unlock a power source millions of times greater. And that is where the upside down starts to bleed through. Okay, so not all atoms of an element are identical. This little dossier breaks it down for you. You've got isotopes. Think of them like different versions of 11 from parallel dimensions. They've got the same identity, the same number of protons, but they weigh a little different because they have more or fewer neutrons. Isobars, they're totally different monsters that just happen to weigh the same. And isotones, well, they share the same number of neutrons. But here's the crucial part. When an isotope has an unstable mix, the wrong ratio of neutrons to protons, it becomes radioactive. It starts to get angry. It starts to scream. Let's move on to file number 2. So now we know what makes an atom unstable. The next question is, what happens when it finally breaks? What are these strange, invisible entities that leak out when they decay? We've managed to capture and profile 3 main types. First up, the alpha particle. We call it the Demogorgon. It's big, it's brutish, it hits hard, but it runs out of steam pretty quickly. It doesn't get very far. Next, the beta particle. Our ghost runner. It's a super fast electron, but here's the twist. It's actually born inside the nucleus when a neutron suddenly flips and becomes a proton. Wild, right? And finally, there's gamma. This is the invisible killer. It's not even a particle. It's a pure, high-energy wave that just passes through almost anything like a ghost. This field report breaks down their stats. Now, I want you to look at those last 2 rows. See that? There's an inverse relationship there. The alpha particle has maximum ionizing power. That means it's great at ripping electrons off of other atoms it passes. But all that damage uses up its energy really fast, so it has terrible penetrating power. Gamma is the total opposite. It barely interacts with anything, so it has minimum ionizing power. But that lets it travel through just about anything. Maximum penetration. Think of it this way. The more of a scene you make, the shorter your journey is going to be. And here's what that looks like in the real world. A single sheet of paper. That's all it takes to stop the Demogorgon. A few millimeters of aluminum foil stops the ghost runner in its tracks. But to stop the invisible killer, the gamma wave, you need 30 centimeters of solid lead. A whole foot. The danger you can't see is always the most deadly. So we know these things get released, but here's where it gets even weirder. This isn't just a leak, it's a fundamental change. When a nucleus spits out one of these particles, it is literally transforming into a completely different element. It's real-life alchemy. So let's go over the rules for these transformations. Think of it like a set of protocols. When an alpha decay happens, the nucleus basically ejects a Demogorgon. It loses 2 protons and 2 neutrons, so it becomes a totally different, lighter element, 2 spots to the left on the periodic table. In a beta decay, a neutron just decides it wants to be a proton. The atom's weight doesn't really change, but its identity shifts 1 spot to the right. And gamma emission? That's just the atom letting out a big sigh of relief, a burst of pure energy after a transformation. It calms down, but it stays the same element.
We're now moving to our most classified file. We are going way beyond simple decay now. We're looking into the ultimate acts of atomic transformation. the violent splitting of atoms, and the incredible process of forging new ones from scratch.
And the key to all this incredible power, it comes down to one elegant little equation from Dr. Einstein. He showed us that mass and energy are really just two sides of the same coin. In every single nuclear reaction, a tiny, tiny amount of mass just vanishes. But when it converts to energy, the result is absolutely staggering. A single atomic mass unit unleashes over 900 million electron volts of raw power.
This is nuclear fission. We call it the Great Split. You take a big, unstable nucleus like uranium-235, you gently tap it with a slow neutron, and it shatters. It breaks into two smaller nuclei, spits out a few more neutrons, and releases a colossal amount of energy. This is the secret behind both our nuclear reactors and the atom bomb. And this is the opposite. We call it the star forge, or nuclear fusion. Instead of splitting a heavy atom, you slam two really light atoms together so hard that they merge into one. This releases even more energy for its weight than fission. But there's a huge catch. To overcome the natural repulsion, because both nuclei are positive and they want to push each other away, you need temperatures of about 10 million degrees. This is literally the process that powers the sun. This threat analysis lays it all out pretty clearly. Fission splits, fusion combines. Fission can happen at normal temperatures, fusion needs the heat of a star. Fusion gives you way more bang for your buck and uses clean fuel like hydrogen. But the biggest difference is control. We can control a fission reaction. We can build a reactor. We have not yet figured out how to control fusion. It's just too powerful, too hot to handle. This brings us to our final file. This immense power we're tapping into, it can obviously be harnessed, but it absolutely must be respected. So let's review its applications and the essential safety protocols we use to protect our world from its dangers. You know, the same forces we're so careful about can also be lifesavers. We use gamma rays from cobalt-60 to destroy cancer cells. We inject radioactive tracers to find tumors. Scientists use carbon-14 to tell us how old ancient fossils are. And of course, industry uses uranium-235 to power our cities. It's a tool, and like any tool, its impact depends entirely on how we decide to use it. And that brings us to Chief Hopper's safety protocols. 4 simple rules. You will live by them. 1. Shielding. Put thick lead and steel between you and the source. Simple. 2. Distance. The farther away you are, the safer you are. Handle things with long tongs. 3. Monitoring. Always wear your film badge so you know exactly what your exposure level is. And 4. Containment. When you're done with nuclear waste, you seal it in thick casks and you bury it deep underground, far away from everybody. These are non-negotiable. That concludes the primary briefing, recruit. But before we can grant you full clearance, we got to make sure you were paying attention. Your final assessment is just 2 quick scenarios. Ready? Okay, first scenario. Our sensors pick up an unstable carbon-14 atom. A second later, it's a nitrogen-14 atom. So, based on your training, what's the relationship between the original atom and the new one? Are they isotopes or are they isobars? If you said isobars, you are correct. Here's why. The mass number, A, stayed the same. It was 14 before and 14 after. That means they have the same weight. But their fundamental identity, the atomic number, changed from 6 to 7. That's a textbook beta decay. A neutron became a proton. Good work. And your final question. We know fusion is cleaner, it's more powerful, so why aren't we building fusion reactors everywhere? What's the fundamental barrier that's stopping us from harnessing the power of a star right here in Hawkins? The barrier is repulsion. Simple as that. Both nuclei are positively charged, and you know what they say about like charges? They repel. To force them to fuse together, you have to smash them into each other with enough energy to overcome that fundamental force. And that requires temperatures hotter than the core of the sun. It is a massive, massive engineering challenge. I want you to remember this. Everything we talked about today, the decays, the splits, the fusions, it all comes down to one simple drive. The universe does not like instability. Those screaming atoms in the upside down, they're not evil. They're just trying to find some peace. Your job is to understand that process and control it. Briefing complete.